welcome back. Today we have a really big treat for you. Miriam is a founding board member of the EEF and still an active board member after many, many years. Her most important quality is probably that she shares the name with my daughter. I did not name my daughter after her, but if I had known her, I might have named my daughter after her. Miriam solves big distributed system problems and has been for 16 years plus, something like that, close to it. So, quit counting. I won't say decades because that just makes it feel really long. All right, so welcome Miriam, and be prepared to take lots of brain breaks.
Hi, everybody. Thank you for joining me today. It was the night before Christmas, all calm and bright. In the middle of a cold freeze, what a peaceful sight. No changes were made, no bugs to repair. Just a quiet night with no errors to spare. But then, out of nowhere, a sudden fright. Machines started dying. OOMs in the night. The night was dark. The silence was deep as the machines fell one by one while you sleep. Every Christmas, every place I work, it's been a party with memory. We stop deploying, we stop restarting, we ask more from our apps, and then, memory just gets dirty. Memory issues are the hardest ones to figure out in the BIM. And more often than not, any other problem you might have, they really just bang in memory. And what I mean is that, let's say you create too many processes, suddenly you're using too much memory. Suddenly, let's say you have external latency. What happens is that your memory increases because your workers are not able to finish their work as soon as they used to, so that memory is hanging there for longer. Let's say you have a scheduler lock. Suddenly, your garbage collection cannot garbage collect your old processes as soon as they finish, and then your memory footprint of your application increases. So it's a good time to talk about memory. So you're ready for next Christmas. I'm Miriam Pena. I'm a board member and founder of the EEF, Erlang Ecosystem Foundation, where I do a lot of stuff, but one of my things I'm proud of is my student program that brought so many of you here. I joined WhatsApp, and seriously, since I joined, I'm really having the fun of my life because I get to play with a system that has at least 2 billion active users. That's not something you get to do every day. At WhatsApp, I focus my time at firefighting memory issues and doing performance tuning of the services. And that's what we're talking here today. Here's our agenda. I'm gonna divide the talk in two big areas. First, I'm gonna do the Big Memory 101, the easy part, in which we're gonna talk about processes, binary ETSs, and a bit of the things we do to troubleshoot and solve some of these issues. And then we're going to go into the deep, dark areas of the Erlang BIM, when we're going to talk about allocators, supercarrier, and a bit more out-of-the-box things that we have no choice but implementing. So let's get started from the very beginning. BIM 101. This is the easy part, so we are all on the same page, OK? When you think about Erlang memory, this is the first thing you learn, and most often than not, this is all you will ever need. Erlang reports memory groups by its purpose. For instance, it groups processes memory on the processes area. Or if you have a binary, and that's bigger than 64 bytes, then, as you know, we share it, and it's reported on the binary area. Same if you insert a binary in an ETS and it's bigger, but if it's smaller than 64 bytes, it actually gets reported on an ETS as long as, as any other term. Basic stuff we all know. So what do let's get a bit into what we do at WhatsApp. The first thing you need to understand what's the memory of your system is a good instrumentation. And I'm sure all of us have telemetry or some sort of color of it by now. We have wonderful per minute or metrics. But the thing is that when we're working with memory issues, the per minute is not enough because your memory issues are per second. More often than not, you have 5 seconds of reaction between something happens, you have that spike, and you're dead. So what we have is an instrumentation per second that basically writes to a file, because it will be too expensive otherwise, every of our memory metrics that we're seeing on the system. And here you can see, for instance, that in the last 5 seconds, we have used around 20 gigabytes of our memory of our system, and you have a breakdown by supercarrier. We're not going to get there right now, but this is basically very useful for troubleshooting. In terms of instrumentation, we have built into our machines what I call a memory outlier detection, which is continuously monitoring for memory spikes or when we are in a situation when we are nearly OOM. And we react to it in various ways. The most easy reaction is just to go through all your processes, check what memory they're using, and if you find any outlier, dump that state somewhere so you can check it out later. But sometimes we can be a bit more funny, and we can even garbage collect our process, or even kill the process if you really have to, not like I recommend you. But we have that. Another super useful stuff that everybody has to have implemented, believe me, this saved my life all the time, is to have an external process monitoring the consumption of your beam. And when it detects that you're nearly OOM, right before the kernel kills you, you kill the beam to get a crash dump. Because more often than not, that crash dump, if you're lucky, will contain information that will help you troubleshoot your memory issue. So we're ready. We have instrumentation, we have an alarm that we are consuming too much memory, and we need to identify what kind of memory is leaking. We look at telemetry. Let's imagine it's ETS memory. Then it's super easy, because you can list your tables for each table, you can list all your keys, you can fetch the data, you can even measure the data and how much byte they take. So that's easy. It gets funny when it's binary or when it's process memory, because then you don't have a lot of introspection tools at the moment. And in those cases, the first thing you do, and I don't like to do it, believe me, but sometimes you just have to bite the bullet, is to do a full-on garbage collection. Go through all your processes and garbage collect a memory of each of them. And you have to do it in a way that you can control how much memory you are reclaiming and also how much memory processes have after the fact. And then you organize those processes. Sometimes you have one process outlier if you're lucky. More often than not, it's not one process outlier. It's really just an aggregation of behaviors. I'm going to give you an example. Let's say you have a request that you want to parallelize, so you're spawning 1,000 workers. And if that 1,000 workers consume a bit of memory, not maybe it's something that you will see one by one, but when you aggregate them together, you actually see several gigabytes of data. And all of them together actually cause that issue. So once you have this analysis, let's pretend that our memory is actually garbage. So what you do is to pick your garbage collection toolbox. And here are some ideas of things you could do. The first one, hibernate your process. Who here is familiarized with hibernation? Yeah, it's one of those semi-hidden stuff that not everybody knows. So you can you can call hibernate directly, I think, and when you do it, you pass around a modular function and some arguments. And what this function does is actually cleans up your stack. So basically, you get the stack of your process emptied out. And you also do a full round of garbage collection. In practice, it's actually 2 rounds. But what happens in practice is that the memory of your process really shrinks because you get rid of all the stuff in your stack, and then you get rid of the heap that you're actually using. And this is useful if your process is going to be idle for a while, because the process will be waking up when it receives a message by executing the function you pass as argument. Otherwise, don't use it. The second thing on your toolbox is to do a full sweep after on your process. And here's when we have to talk a bit about deep stuff. Let's see how a process looks like. High-level overview, we are abstracting it a bit. But that basically, every process has this big space of memory that's unique and is owned by it, that has a stack and a heap, and they grow towards each other. And then eventually, when they meet, and there's no more space, forget the one on the right, you trigger that garbage collection. That's how garbage collect works. You trigger it when you don't have more space for the stack or the heap. There's two types of garbage collection. There is one that garbage collects only this gray area, which is called the junk heap, and there's a second one that collects the whole thing, which is the full-on garbage collection. And then how it works is that most of the time you're doing just garbage collection of here. So whatever you have here will have to wait, I don't know, thousands, I don't know the number, of this minor garbage collection until this happens. So when you do this option, the full sweep after, what you're actually doing is to tell the process how many minor garbage collections you have to do until you major garbage collection. And if you're very crazy, you can put it to 0 and do garbage collection, major garbage collection all the time. I do not recommend, but sometimes it saves the day. Yeah, and the second part area, so just all you know, when you do this garbage collection, you start copying every little data to another part of the heap. That's how we compress the data, and when you release the memory, that's why it looks smaller. But you actually, when you reserve a memory process, what I mean is, you have a process, and it has a memory. Half of the memory is actually not used. It's just because we need garbage collection, and we need that space there for it. Let's go on third tool in our toolbox. Spawn more processes. And now you're like, how would that work? You just told me if I spawn more processes, I consume much memory. How is spawning more processes going to help me? And the thing is that, let's say you have one process that does this a massive amount of work, which is a lot of terms that are nested on each other, creating this massive structure. If you have to garbage collect, every single little thing is going to take much, much longer than if you just kill the process and reserve the whole memory at once. So sometimes we tend to reuse processes and it's actually biting us. It's better just to spawn a process, do this big chunk of data, and kill the process. But sometimes it's just, yeah, seems contradictory, right? But it's really worth a try. Because sometimes what you happen to have is too many processes that are competing for your scheduler. And that causes the processes to start locking on each other. And that delays garbage collection and is creating a whole lot of mess. I'm going to give you an example that I had the pleasure to experience in production not long ago. One of my favorite metrics is scheduler utilization, which you can think about like how % of your schedulers are actually busy on a given of time, so a bit like a CPU utilization. So you can see a system that was relatively chilling at 60%, and in 1 second after, it went to 90% scheduler utilization. That was a lock. And when that lock happened, just a little bit after, our memory consumption started screaming until we ran out of memory. Let me zoom in just a bit. So it's more clear. 60 to 90, memory increasing. We reduced the number of workers. We actually reduced 80% of our workers, and that removed the lock, which removed the issue. So it was interesting. So we're done with garbage collection, and let's go back in time. We do this garbage collection thing. We imagine it's not garbage collection, like it's memory we're actually using, and then it's like, where is my memory? And again, let's look at our process, which we're familiarized with at the moment. If the process it looks like this, your memory, most likely than not, is going to be here. Referenced by the stack, the mailbox with your messages, or your process dictionary. And if your memory is on the process dictionary, super easy. You get the process dictionary, and you can pick every key, the values, and weight it, and it's there. And the same with the mailbox. But if the memory is on your stack, there's not much you can do. Because you can see your stack trace. You know what your module and your function is executing, but you don't know the variables. and you know the names, but you don't know what it's there, and you don't know how far back. You don't even. So in those cases, there's the Beam book suggests something that if you import a library, it works, and it's probably working. I never tried. But for us, what saves us is to actually inspect the crash dumps. And we have our own parser, and this is how it looks like. For instance, here, I hidden out some areas because it's proprietary information. But you can see this is a list of our processes, and this is the memory consumption. This is very similar to our famous crash dump viewer. But we have also this section that sorts by binary. And here you can see a process with around 4 gigabytes of data. And here you can see the decoded stack of the process. And let me zoom in again. You can see that the Gene server is receiving a response with a binary that's 600 megabytes. And it's like, what? A whole block of 600 megabytes continues as a variable. Yes, we were basically concatenating binaries without thinking much about it. Another one, this is what I told you about the grouping the processes. One process is not a memory outlier. You group them together, then you see something here. You can see how there is some supervisor that has 500 children. There's actually 16 of them, each of them consuming 4 gigabytes in data. And yeah, the tool allows you to see the children and navigate through it. It's actually really cool. Let me zoom in so you enjoy. Oh, there, yes. OK. We are working on making this tool open source. We're finalizing the details, so hopefully I can soon share it with everybody. So let's go into common patterns of parallelizing requests. This is my favorite. Remember when you study interviews, we always do the computational complexity, and then we do the memory complexity. And there's this funny pattern in which, let's say you have a request with a lot of potential for parallelization. So you spawn 10,000 workers, and the argument of the request is this big block of memory. If you copy this block of memory 10,000 times, suddenly this explodes. This is a m(n) squared, or total processes for total request memory complexity that we need to avoid. And sometimes we can think that if we hide it on a fan, we can work around it, but we're not. We still copy the whole thing. So be careful for that. More often than not, you can actually just extract the part of that argument that each of your workers needs, so you actually send just the data it needs, not the whole thing. Another common mistake is when we do big requests, and this is fascinating in my opinion. Let's say you have one process that receives this big work, like you said, a multi-get, and instead of parallelizing, you decide that it's going to do the whole thing. So then you have a process whose heap needs to grow to accumulate for all the intermediate steps, and eventually you have a process with a gigantic heap that its work finalizes, and when it's done, you have the situation in which that memory is going to be there until the next garbage collection. That might or not happen right away. And if it doesn't happen right away, then you have one process with a big memory footprint. And if that happens in more processes, then you have a bigger memory footprint of your application. So splitting those big requests into smaller chunks, you actually make your memory patterns a little bit more stable, because each process will work with a smaller memory footprint. And you actually reduce your latency, too, more often than not. OK. So is there anything else we can do to prevent? Before we move on, 3 latest tricks. First one, you can limit the maximum heap size of your process. It will be killed if it goes beyond, but sometimes it's better to kill a process than to kill a node. You can do more aggressive garbage collection. We talk about hibernation, a full sweep after, but then you can also just call manually garbage collection after doing that big, gigantic request. You can do that. Yeah. And then the third option, why not work for every case? But you can opt your service or your node to leave the load balancer or throttle request when it's approaching OOM. And then when it recovers, you can go back in. And with this, we have a pause. Now we're ready for the fun part, the intense stuff. We're going to talk about allocators and supercarrier and a bit of the crazy stuff, so we're all on the same page. Do you remember our memory function? One very important takeaway that is very often very confusing for a lot of us is that it represents the memory that is used by the beam. And by use, I mean that I have actually put some variable data in the very near recently, meaning it's not garbage collection yet, or it's actually being with data right now. And what your OS reports as the memory that your beam is consuming is much, much, much bigger than that. You will see that a lot, and you will think, why? So the memory in the beam, as we said, is specialized by type of data it stores. And in Erlang, for every type of data, we have something which is called an allocator, which is specialized again. Objects of the same size tend to have a predictable object size. Think about Tetris. Is that it? With the 4 blocks, you go down. If you're good, you manage to have it all compact. There's a whole once in a while, but for the most part, you can keep it coming. So that's the goal here. That's the perfect alignment of memory, so you have very few of those little holes called fragmentation. That happens when you put objects of the same size in the same way. Now imagine that in your Tetris, you have this very weird shape right there falling, and then you have to put it somewhere. It's going to be really hard for you to fill those gaps. There's lots of allocators in Erlang, specialized by type of data they're working with. These are the 4 that I find more often than not I need to look at. The heap allocators specialize, among many things, on storing your processes data, your processes heap. The binary for those big binaries, you can guess the rest. If you add these 4 allocators and many other stuff together, you're actually really close to what your OS reports as your memory consumption. Up to here, okay, right? Yeah. So allocators store memory in something called carriers. That's where the memory is placed. So imagine you need to store data for an integer. You need a little block of memory to put that integer. You ask one of your carriers to put that. And if the data that you're storing is bigger than a threshold, which means very big data, it goes to what we call the single block carrier. And that stores blocks that are super unpredictable in sizes and bigs. But if it's smaller than a threshold, it goes to the multi-block carriers, which has sizes that are increasingly, I think, they're smaller and they increase in a way that is very easy to put them together, block them together. If you want, okay, now it's gonna get fun. So we have, for each type of data, we have an allocator. We have many types of allocator. Now, there is one allocator, one for each of your schedulers. And you know, we have one scheduler typically for each of our cores on our machines. So in the practice, if you have a machine with 40 cores, you have 40 schedulers. So you have 40 heap allocators. This is a binary, 40 binary allocators. When a program is running, typically tends to compact its work. So typically the first schedulers are the ones that are actually busy, and the other ones are just chilling there, waiting for a spike in computation. But if such spike happens, then they're going to have to allocate data. And think about it in a way that you have, each allocator has their carriers, which means they're going to use if they need to put some data somewhere, they're going to put it on their carriers. So you have a spike here, and you allocate this massive amount of data, and after a while, the spike goes away, and the allocator is idle. You find that you have one scheduler with a lot of memory that is free, but is allocated to that carrier that cannot be used by any other carrier, and that kind of is not nice. So the Beam has something which is called a pool, which is some sort of abstract concept of schedulers sharing their carriers with each other when they don't need them. I'm not going to get deep into that because that's a whole wonderful world that we wouldn't have time to talk about even if we had a whole day. But the idea here is that there is instrument is a module you can use, and there's two wonderful functions there. One is carriers, the one we're seeing, that if you call it with one particular scheduler and one particular carrier, you can see one by one all your carriers with whether they are in the pool, whether their size, 4 megabytes, how busy they are. This is a brand new Beam, so they're all free. And here is a number of blocks of this size. So we have 124 blocks of 128 bytes. These first ones are multi-block carriers because you see they have many blocks. This one is a single block carrier. Again, it's a fresh new Beam. All here, yeah? Okay. This is another carrier. It has a lot of fragmentation. And when you actually call the number of carriers, you see pages and pages and pages and pages and pages and pages of this. And you have lots of fragmentation because we have thousands of tiny free blocks of 120 bytes. But if you add them together, it's not a lot of data loss, but there is something here. But personally, what worries me more is that I also have pages and pages of carriers that are mostly empty because they have all sorts of free blocks of all sizes. And when I see that, I am like, why are you not reusing your carriers a bit better? Why do you keep allocating new carriers to put this memory in instead of, yeah. Okay. Let's go on. At WhatsApp, okay, so the story here is that before I move on, there's one function called carriers, there's another one called allocators that gives you the same view with the block size, with the user sizes. And the carriers, when an allocator needs a space for a carrier, they typically call the operating system for the data. You have two options. You can do an mmap by using the message allocator, and you can do a malloc with the sysallocator. At WhatsApp, we had really bad performance doing this. Basically, we had stuck schedulers calling mmap when we had a very high load. So we couldn't use this pattern. And we used something else, which is called a super carrier, which is a mega allocated data that is available at startup and can be used to actually request big chunks of data. And this is what a super carrier looks like on an actual live node. Think about it like a big block of virtual memory, continuous. There's two areas in it. The lower area is where we store our predictable sizes multi-block carriers. You will see the grays is free spaces, as you see it's really compacted and nice. The SUA is the single block carrier area that stores these anomalous sizes, Tetris pieces, and that has a lot of holes. Lucas has recommended that I think if I quote him right, 80% of your memory should be on the lower side rather than the big side. And over time, as you need to allocate more memory, for instance, you allocate 4 gigabytes continuous block of memory, then your supercarrier will have this continuous green area. That's one gigantic block. And when it's done, it gets released, it goes back for anybody to use. But sometimes it just keeps growing until you get like this. And I personally think there's a lot of carriers fragmentation here, because you see a lot of white spaces, but there's no one continuous block of data that you can actually use. But when you run out of memory, we have opted to call the operating system for one last call, have a few gigabytes extra, and eventually you die because you run out of memory. Instrumentation. OK. So a lot of this data can be fetched with the recon alloc module from Fred, or you can just call system info. You can see how much memory each allocator is actually using and how much memory is allocated. For supercar information, you have there the sizes of each area, how many phrase segments, blah, blah, blah. These are super important. I love them. Get familiarized with them to get your free block sizes and your free empty sizes. So you can, because with that data, there's a lot of options you can do to play with how your data is distributed if you're experiencing fragmentation. And there's a lot of articles that talk about it, so I'm not going to talk about any of that. Remember our memory outlier detection? When we started experimenting with allocator issues, we added a couple of reactions. One of them is to store a snapshot from recon alloc that gives you the state of your allocators at that time. And the other one is storing the fragments of supercarrier, which is something you can do by calling this non-documented, not recommended, never use it function that we reverse engineering by looking at the actual code. It's mostly fine to call in the way that there is a red flag tree there, and you lock that red flag tree to get your free segment, so that's fine, always, except that one day in which I was playing with my thresholds. Remember the single block carrier and multi-block carrier thresholds? I was trying to put more information in the free size, crazy size areas in the top. And that day, I created a 90% fragmentation on the super and aligned area of the supercarrier. So this will be memory allocated versus memory used. So that one day, I did that in production. And I think I created like thousands of free segments. It was, and the beam kind of died every few hours. Yeah, so I was like, oh, let me check how the supercarrier is. So I did that, and then the beam freeze because I created a kind of deadlock there. So yeah, don't do that day, but otherwise it's fine. OK. Troubleshooting. With the metrics, it's easy to see the difference between allocated and used memory for each allocator and draw conclusions from it. We had a few cases in which we have to deal with allocator fragmentation. And I'm going to talk briefly about three cases of those. I did not personally experiment this myself, so my coworkers did. So I'm going to do my best to translate their amazing work so we can share with you. The first story is about a RocksDB database that is mostly stored to stores bundles of messages. And my colleague Henry gave a talk about this last year. I recommend you to watch that talk. And he's the one authoring this little bit of research. Basically, this database is implemented as an Erlang NIF that uses glibc malloc to do these allocators. And it could happen directly calling to it, and sometimes it happens through the sysalloc. And the system works really well, but historically, the memory footprint was growing. We had this gradual memory growth that was leading to OOM issues. So we basically had to, in other words, restart our machines preventively every time we had a code freeze so we wouldn't die in Christmas. They tried a lot of things out, but the one thing that they tried that was a bit out of the blocks that actually fixed the issue was to replace all the calls from the beam from malloc to use another library called gmalloc. Jmalloc is a malloc implementation that is very good at avoiding fragmentation and is very good at scaling concurrency. And this allows us to drop 5% of CPU, and we avoided that fragmentation. So now the memory footprint of the application is very stable, so we don't need to do restarts anymore. That was great, but we had another issue. And this was related to a transfer of set of data between hosts. So imagine you put a host lab, you want to transfer data. You have this big spike, and it's a 2 gigabytes per second transfer of data. And once in a while, when this happens, we would OOM. How this was implemented was by having, so this down there are each of our nodes connected through the Erlang distribution. So we basically had to copy one file. From the file system, we were passing the data through Erlang distribution to the other data and storing the file. And what we suspect happening is that the beam was not able to keep up with memory deallocations because of the delayed by allocator behavior. And yeah, we talked about it a bit before. So what do you do if one allocator gives you trouble and you can't do your work? You stop using it. So what we did was to opt to avoid the binary allocation altogether. We stopped sending the data through dist, and instead we created a second socket that is using, on the sender side, KTLS and sendFind syscall to transfer the data directly from the file system to the network stack and within kernel space. So we're not going with the data to user space. We stay right up there. We transfer the data. And on the receiver side, they added a NIF to support pipes, and they did a splice syscall, allowing the data to flow directly between the socket and the file systems, again, without passing through user space. So basically, we avoided fragmentation on an Erlang allocator by not using it. This fixed the OOM. This is the third story. And this one is ongoing investigation. It's a story of a less recently used cache that created a 45 fragmentation in just 3 days. And it used to be way worse. We used to die every few hours. But we changed the way we store our data. In particular, we moved from a key that is a variable binary in size, so a binary that could be longer or shorter. We moved that to have a key that is an integer that is fixed size. And because of that, we actually, we avoid a lot of fragmentation. We still have some, but bigger went away. And we are brainstorming things to do. And the way I see it is that the Erlang allocators work really well most of the time, but sometimes you're just in this 0.1% of the cases where they don't work for you, and you have to think a bit out of the box. And one of the ideas we are actually toying with is to replace the ETS allocator with Jmalloc and see how that goes. All right, so takeaways: have great instrumentation per minute, per second, add metrics of how much memory your allocators are using. Become a crash dump expert. I know they're scary, but it's not that bad, really. They're actually fun once you get familiarized with them. And for that 0.01% of the cases when big allocators cause trouble, you can try Jmalloc. And this is it. Thank you.
We have an online question. You ready?
Yeah?
Okay. I'll back up.
Easy one, please.
Okay, we'll try. This is from Conrad Taylor. I have used C-Advisor or Grafana and Prometheus to visualize resource utilization like memory, CPU, and so on. Are there any other off-the-shelf tools that you would recommend to monitor memory and other resources?
I couldn't hear the words. Sorry.
Too fast. Okay. Yeah. Are there any off-the-shelf tools that you recommend for monitoring memory and other resources?
You mean telemetry libraries? Or the actual
visualization?
For visualization, No, I would just, I mean, we did this wonderful visualization for the supercarrier, but for the most part, it's just whatever you use for telemetry, I think will be the right solution for you.
Thank you. Excellent presentation. I've been in some of those trenches before. I was wondering if you have recommendations about configuring supercarriers on production systems. What should I be thinking about the workload while configuring that value? And the second question is, once I use these tools to figure out how my memory is behaving, how do I get to parts of the code? Because I can have profiling information, I can have memory information. How do I mentally join these two things? Because I've been doing that and it's very manual for me. Thank you.
Okay, so my experience is, in general, when you enter the world of allocators, there is no one rule that works for everybody, because every system will have massive different behaviors on how much data is used for its sizes. So sadly, it's a lot about just testing what works for your application, which is frustrating and time-consuming. And it's for the second one. I think I'd rather sit with you and go through those cases together. So if you wanna, after the talk during the day, let's walk. So that if anybody else is interested, we can talk together. It's just really very specific. I want to really understand what he did. Thank you.
Anybody else?
What percentage of free memory do you aim to keep on your servers when you're not nearing OOM?
What percentage of?
Yeah, it's like what percentage do you want to have most of the time for your Beam instances? What percentage free?
It really varies. There is some services that the memory, like a database, has a memory footprint that's very stable. It's not proportional to the traffic you expect. So they will have a different value there when it's depending, versus a service whose memory footprint increases as you increase traffic. So it really depends on what your expectations of your service is.
This is the last question, and then we're going to go get food.
Okay, so it's not a question. We also have similar issues with the OOM killer. So we gave the advice, disable it on the system level. And then the Beam will abort whenever it runs out of memory when malloc fails.
Okay.
So that's another option. Fail in a different way.
That sounds fun.
Yeah, exactly.
All right, well, thank you, Miriam.
Thank you, everybody.